Now, first of all, we'll see these are the three questions that we will be answering in this particular part. What is the difference between a standing wave and a traveling wave?
Mm-hmm.
Second, how does the form of standing wave depend on the boundary condition? So there are something called boundary condition. There are
Okay.
boundaries. And for a standing wave, boundaries are very much important and they are required. Third part that we'll try to understand, how can the application of force result in the resonance with the system? So basically that's the resonance of something else. But first let us try to understand what is standing waves.
Okay.
Right. Now, let me give you a simple example here. Imagine I have a container which looks like this, and it is a metal container. So that means it has a very good property of to reflect wave. Okay.
Mm-hmm.
Metals reflect wave. So let's imagine I have this particular thing which is reflecting wave. Even wood reflect wave very well. Okay, so better than metal, wood reflect waves better. So let me consider I must have seen flutes, right? Flutes.
Yeah.
Okay, so it's done because flutes are very good in reflecting waves and forming standing waves inside. So let's
Okay.
I have a wood and I'm sending a wave. This is my wave. Okay.
Mm-hmm.
So as soon as the wave hits one part of the other end, it is the starting end, and this is the another end of the pipe. When it hits the pipe, you know what happens? It gets reflected. So what is happening here is getting reflected.
Yeah.
Okay, it's getting reflected.
Mm-hmm.
Now you see this is the crest of the incoming wave. Incoming. Remember, there are two waves. In this formation, you are having two waves. One is the incoming wave, which is the actual wave, or the other one is reflected wave, which is getting reflected from the wooden end.
Okay.
So so I will probably use a different color code. So for incoming wave, this is the crest, this is the trough. This is the crest,
Okay.
this is the trough. For an incoming wave. And this is the trough. Second, I will do some, yeah. And this is the trough for the reflected wave which is going out, and this is the crest of reflected wave, this is the trough of a reflected wave, and this is the crest of a reflected wave. Does it make sense now?
Yes.
So how did this formation occur? This formation occurred because of reflection at
Mm-hmm.
a boundary. This occurred because of reflection at.
A boundary.
So now I told you, right, boundary conditions are very important for a standing wave. So we have a boundary here which is causing the reflection. And this
Okay.
boundary has some conditions, mathematical conditions, which we will see. So this is a
Mm.
basic thing which I'm showing you. You have an incoming wave, you have a boundary, then you have outgoing wave, and incoming wave and outgoing wave are built in such a way that they have a phase difference of 180 degrees. That means in the place of crest trough comes, in the place of trough crest comes. Can you see which is happening right now?
Yes.
Wherever the crest of incoming wave, the trough of outgoing wave is there. Crest trough, crest trough. Now I told you this crest trough can have a nullification effect, destructive interference, right?
Yes.
Have a nullification effect. But right now here, it it forms a point like this. Now, if you see at these 2 points, crest and trough, it will
Yeah.
be vibrating like this. Okay, so it will be like this, crest trough. It will be vibrating.
Okay.
But look at this particular region, very interesting part. Look at this particular region, this region, this region.
Yeah.
These regions don't even move.
They stay in place.
They're in the same place.
Yeah.
The movement happens only in the crest and trough like this.
Okay.
It doesn't even move. This formation is called a standing wave. That's why the wave doesn't appear to move to you. Understood?
Yeah.
This formation is called as a standing wave. That means the wave doesn't appear to move. The wave doesn't appear to move. But
Mm-hmm.
how did that form? It formed because of reflection of wave, and the phase difference of the reflected wave is 180 with the actual wave, and it creates
Yes.
a pattern. And this pattern is basically called as, what do you call it? The standing wave.
Okay.
This is the pattern of a standing wave. Now, standing wave has a different, there are some applications of standing waves also, which we call it as beats and all. But yeah, we will see in detail. But you understood, right, what we are going to see here?
Yes.
We are going to see waves traveling inside a container, wooden container,
Yeah.
like we call it as pipe, open end pipe, close end pipe. So open, close refers to the boundaries only. So wave is
Okay.
going through a pipe and is going to create a standing wave pattern, and all those things we are going to understand now. So the introduction part is clear to you.
Yes.
So basically, this is standing wave. Now let us try to understand one by one in detail. Let's go in each thing in detail. So see, there are so many things that you learn. Nature and formation of standing wave, nodes and antinodes, relative amplitude, phase difference, standing wave pattern, string and pipe. Yeah, there is a standing wave formed in strings separately. There is a standing wave formed in pipe separately.
Okay.
Also, we will see. Resonance, natural frequency, driver frequency. I think we do not have beats here. Beats is not there. Beats was there the previous syllabus. Let's see.
Okay.
Okay. Now you see formation of a standing wave. Okay. Look, you have two waves here. Okay.
Yeah.
Let us talk about the interference. When crest and trough match, you have constructive interference taking place, and the resultant is going to have a higher amplitude, as you can see.
Yes.
Red color, blue color are two waves. The black color is the resultant one.
Yeah.
As the difference between the crest and trough keeps increasing, the height of the resultant keeps decreasing.
Yeah.
And as they go completely 180 apart, you see the resultant is almost zero.
Mm-hmm.
Resultant is almost zero. This is what the standing wave looks like. I showed you that the example of pipe also.
Yeah.
Okay. Here, the blue color wave and the red color wave, they have a phase difference of 180.
Yeah.
What is this phase difference basically?
It's like so the two waves are starting from different points, and that difference is what the phase difference is.
Very good. They are actually starting from different points, or different points in the graph, but I say different point. In that graph, basically the different point refers in different angle, right?
Okay.
Like this, if I tell you that this is a graph, this is 0, this is 90, this is 180, this is 270, this is 360. So one wave is this, but
What?
one wave is starting
Yeah.
from 0 and it's going like this.
Yeah.
There's another wave which is very similar, but it's starting from here and going like this. What is the phase difference between?
Phase difference between these waves would be pi over 2.
Very good, 90, pi by 2. All right, because look at the starting point. The difference between the starting point is pi by 2, and that's how you basically get the idea of phase difference.
Yes.
And for a standing wave, it is very much important for us the phase difference should be 180.
Yes.
And the secret lies in one more phenomenon, which is called reflection.
Mm-hmm.
You know what reflection is, right? But I'm going to tell you something about reflection you wouldn't have known before. What is
Okay.
reflect? What is reflection of wave?
I don't know about well, it'll hit the point. and then it'll go back.
Bouncing back, right?
It means, yeah.
So light falls on a mirror and bounces back.
Yes.
Light falls on a mirror and it bounces back. Okay. So that particular phenomenon is called reflection. But reflection has a theory attached to it. Reflection has a rule.
Okay.
In terms of wave, you know there are two rules of reflection: angle of incidence, regular angle of reflection. Incident ray,
Yeah.
reflected ray, in normal all lie in the same plane. But
Yeah.
in terms of wave, there is a rule, and that rule is after reflection there will be a phase difference of 180 degree pi.
So
Okay,
after reflection, there'll be a phase difference of 180.
pi. Yeah. Okay. So that is the reason why in that pipe example, when the wave got reflected, there was a phase difference of pi in that
Okay.
case. Understood? And that phase difference pi is what creating the standing waves.
Okay.
So I hope you're understanding the standing waves, how they occur now.
Yeah.
There is more mathematical parts into standing waves, which we are going now. Okay, so this
Okay.
is kind of outlook of a standing wave. What are they and how they form? Now we are going to understand what are the parts of a standing wave. Red wave, blue wave. Okay, they are superposed. As I know, superposed means superimposed. You
Yeah.
form a standing wave. Okay. Now there are some points with zero displacement. Okay. There are some points with zero displacement in a standing wave, and those points are called nodes. These are the nodes. I told you, remember the points which do not have
Yeah. The ones that remain still.
yes, this point. These points are called nodes in a standing wave. Understood?
Yes.
Nodes. And these points which are maximum are called antinodes.
Okay.
So these are the only two parts of the waves. That's all.
Okay.
Normal wave does not have it. Normal wave has only crest trough and all.
Yeah.
Nodes and antinodes, only standing waves I will have. So nodes and antinodes are the part of standing waves.
Okay.
Zero displacement point. Okay. Right. So I think these are the concepts which, and the positions where the displacements are largest as possible is called antinodes.
Okay.
All right. Great. Nodes, antinodes. So this is how it looks like. You see, nodes, antinodes.
Yeah.
Fine. Okay. Now, few things we should know about the phase of the standing wave. Okay.
Mhm.
Between two adjacent nodes, all the particles move in a phase with each other. Do you agree with that?
Yes.
Between two adjacent nodes, all the particles move in phase with each other. Let's look into it. Why? There are two nodes, isn't it? N and N dash.
Yes.
So all the particles here and all the particles here, they are in phase with each other.
Yeah.
With each other. Okay. Second, in adjacent nodal region, particles are 180-degree out of phase. Where is N dash and N dash M? Okay,
Yeah.
fine. I'll tell you what is this. Now, the particles which are here and the particles which are here, between them, there's a phase difference of 180 degree.
Okay.
So I'll tell you again in a very simple way. Okay. All the particles here are in same phase with each other.
Yes.
All the particles are here are also in same phase with each other.
Mm-hmm.
But when you compare these both, they both are 180 degree phase. They both have 180 degree phase difference. That means
Yeah.
these people are having phase difference of zero. They may be having an angle of 0, 0. they are having an angle of 180, 180. That means they both are
Yeah.
phase with each other.
Yeah.
But when you compare between them, they both have a phase difference of 180.
Yeah.
The thing that you should remember between the two adjacent phases.
Okay. Yeah, that makes sense.
All right. Yeah. See, you should know all these points because they might ask questions related to it. Maybe they won't ask problem on this, basically.
Mhm.
But they might ask you some like logic-based question or MCQs also can be asked.
Yeah. Or some definition-based questions that could
Yeah,
appear.
definition
Yeah.
based very less, but MCQ based question can like they can give you one particles oscillating here, but what is the phase difference between these two particles they will ask. And so
Okay.
that time you need to answer using all these, things.
Yes.
Next, there is therefore only one value of phase difference between nodal points. That's what I told you. Between two nodal points, if everyone will have 0, 0, 0 angle, so there's only one value of phase difference they are going to have.
Yeah.
Now, these last 3 points are very important. The distance between two adjacent nodes or antinodes is equal to half of the wavelength of the original wave.
Okay.
Mark it. Very important. We will see that how. How is it? Okay. The distance
Okay.
between two adjacent nodes or antinodes is equal to half of the original wavelength. Let us see how. The distance between two nodes. Don't you think that this is a single half wavelength?
Yeah.
So this is full wavelength, isn't it? This is full wavelength.
Yeah.
The distance between two nodes is half the wavelength.
Yeah.
Or the distance between two antinodes is also half the wavelength. How much?
Mhm.
Let me ask you one question. Let me see.
Okay.
How much is this wavelength? How much is this?
It's a quarter of the wavelength.
Very good. And how much is this?
That's also a quarter.
When you add the quarters, what you're getting?
You get a half.
Very good. You get a half a wavelength. So if I want to get full wavelength, that is going to be node after adjacent node. That's my full
Yeah.
wavelength.
Yeah.
Like my node after the node. How do I call it? It is the consecutive node, not what word can I use?
You say it's a second node.
Second node, yeah. So the distance between that current node and the second node is the wavelength. Okay, so all these things are very important. Make a note because questions will be based on these things only. All right.
Yeah.
Next point. The distance between two adjacent nodes is equal to the standing wave oscillates with the same frequency as a traveling wave. Yes, frequency does not change. Phase is changing, but frequency will never change.
Yes.
Standing waves has the same frequency as the original traveling wave. All right. Finally, lastly, within n and n dash, that means between two adjacent nodes, there are no 2 points which will have same amplitude.
Okay.
Okay. There are no 2 points which have same amplitude, which can vary between 0 to maximum. You see here. Between, yeah, between these two regions, between
Yeah.
these, there is no point, no 2 points which will have same amplitude.
Mm-hmm.
Now, but they all are having same phase. They all are having same phase. Now the question
Yeah.
is, imagine, let me take a position here.
Okay.
At which position in the standing wave will the amplitude will be same?
In the middle.
How far should I travel to get the same amplitude?
Oh, half a wavelength.
Very good, half a wavelength. That means if you travel half a wavelength, you will reach this point. So what is the
Yeah.
distance? It's 2 points, half a wavelength.
Yeah.
Okay. So now you understood the structure of a standing wave.
Yes.
Is standing wave becoming clearer and clearer for you?
Yes.
Okay, slowly, that's how you enter the any concept in physics. You make it clear, you make it clear, you make it clear. You should be able to imagine it. You should be able to structure it in your mind. After that, the
Okay.
questions are very simple. Okay. Standing wave, visible or standing wave. Okay. Right. Now let us go to the formation part. We will do these questions later, or yeah, we'll do that later. We have 1.5 hours of this. Now let us try to understand the formation of a standing wave. And we will try to understand what are these harmonics. Now, there are few names that you might have to memorize. Okay.
Okay.
What is first harmonics? What is second harmonics? And all those things you need to memorize now. So, yeah. So, first of all, I told you in a simple case how a harmonic, how a standing wave can be formed. That is by reflection, and there's a phase difference of 180°, and that is how the things are formed. What do you call the standing wave is formed?
Yeah.
Okay. Now, once. So I think standing waves, if all right, known as the first harmonic, second harmonic, respectively. Okay, there is something called harmonics, which we'll see what is it.
Okay.
First boundary condition of a wave. Now I told you boundary is something very important for the wave. Okay. Now
Yes.
we are going to work with string, not with a pipe. Okay.
Okay.
We are going to work with string. You know that any string can have waves on that. If you vibrate the string like this, you will form a wave in the string.
Yeah.
Okay. So we are going to deal with that now. So first boundary condition, fixed end. Okay.
Mm-hmm.
So that means, imagine I have a wave which is forming like this, and this particular end is fixed. Can you look at this point? This is not going to move. It's called fixed end.
Yeah.
Now, fixed end plays the exact role of a closed boundary in the pipe.
Yeah.
Exact role of the closed boundary in the pipe. That means it changes the phase by pi.
Yeah.
Okay, so when you start a wave here, the wave will eventually get reflected and will come like this.
Yeah.
So it's going to eventually do the work of a closed boundary pipe. So it is a fixed end. So the fixed end cannot move, so displacement always must be zero. So here there will not be any displacement, and there will be a phase difference of 180°.
Okay.
And the reflected wave moves opposite direction from the fixed end, and an opposite displacement to the incident wave. That means opposite displacement means you are having phase difference of 180°.
Yeah.
And is free end. Yeah, we will see the mathematics of everything, but we will first try to understand the difference.
Okay.
Then we will go to the mathematics. See, there are a lot of mathematics involved here. Second is
Oh, wow.
called free end. Second is called free end. Free end means this particular end is there, right? Which was fixed initially. This
Yeah.
part can actually move up and down.
Okay.
So it's like you are it's like you are having a pole here, and you are fixing a string to a kind of ring. So what happens when the wave comes, the ring can move up and down, isn't it?
Yeah.
So that's a free end.
Okay.
And here, if the string is kind of tied to a stick, then that's a closed fixed end. Understood the difference?
Yeah.
One is a free end. Fixed end we have seen, its boundary condition is that it creates a phase difference of 180.
Mm-hmm.
Next is the free end. Now what happens in a free end is the free boundary condition is different. In this case, the reflected wave is generated as a particle in the medium and returns to the equilibrium position. This means the reflected wave is moving away from the end, will have the same shape as the incident wave and will not be inverted or reflected. not be inverted on reflection. That means the phase difference
Okay.
is low in this case.
So there's no phase difference in free end.
Yes, there is no phase difference in free end. Okay. And it will
Yeah.
have the same shape as the incident wave and will not be inverted on reflection. All right. Now let's go to the mathematics part.
Okay.
This that you are seeing is two fixed end. Can you see? Both the ends are fixed.
Yeah.
Now, when both the ends are fixed, the only possible way to move the string will be like a guitar. Like guitar is an
Yeah.
example of both the ends fixed.
Yeah.
Guitar is an example of string with both the ends fixed.
Yeah.
Now, look at this diagram. You can see waves vibrating.
Yeah.
What's the difference between these three waves?
The number of oscillations present.
Very good. Number of oscillations present. So what is happening here?
So in the first one, it's just been like the wave has been pulled up once. In the second one, it's been pulled up so that it's going like this way.
Very
And
good.
in the third one, it's been pulled up high enough that there's three so there's 1.5 wavelengths forming.
Very good. So have you studied this before?
No.
Good. You are catching to the point perfectly. Okay, so very good. So what you explained is very simple, and yeah, it is actually very simple. Visually, you understand it's much more simpler. You know,
Okay.
standing waves, usually you need to see visually and understand better. Then only you will understand the mathematics part. If simply
Yeah.
you try to learn the mathematics part, you will never understand what is standing waves.
Okay.
Physically, to see first. Let's look into it, what is happening. There are two ends. First of all, let me tell you, these are the first three harmonics of a standing wave in a string, both the end fixed. Again, listen
Okay.
to my statement. This is a standing wave of a string with both the end fixed, and it is a first three harmonics. N is equal to 1, first harmonics, 2, 3.
Okay.
Let's look at now the length of the C. In all the cases, it is the same string that is being used, which has a length L.
Mm-hmm.
All the cases, it is the same string that is being used, which has a length L. Look at the
Yeah.
first. If you look at the first case, you will observe that you are actually having half a wave for length L. That means half a wave for length L. Does that make sense to you?
Yes.
Yeah. You have half a wave for length L. So this is the relationship lambda is equal to L by 2. And
Yeah.
frequency is number of waves per second. So frequency where here the C is going to be the speed of actually it should be the speed of the wave.
Yeah.
And we have studied that. We have studied speed is equal to frequency into wavelength. Yes or
Yeah.
no? So here the wavelength is 2L, right?
Yeah.
Here, the first harmonic frequency is velocity by 2L. Here
Yes.
it is given by C, but here I'm just writing it for you to understand that this is velocity of the wave.
Mm-hmm.
In the second case, you see, it's called the second harmonics. No, it's not called second harmonics. It has a different name. I'll tell you different names.
Okay.
In this case, you see, you have a complete length of wave.
Yeah.
In this case, L is equal to lambda, and your frequency is equal to velocity by length. In
Yeah.
this, you have 1.5 wave for the length L. So your L is equal to 3 lambda by 2. So frequency is equal to 3C by 2L. It's actually F3, okay? 3C
Yeah.
by 2L. Did you understand this particular relationship in a wave? This mathematics, you understand?
Yeah.
Frequency, speed, wavelength relationship, two ends closed string.
Yes.
You should know it is for two ends closed string, length L, and you have frequency, wavelength, and speed relationship.
Yeah.
You should know the boundary conditions also. The boundary condition is two end fixed.
Yeah.
Okay. Now let me give you the names. Let me see if they are, yeah. First three harmonics. Yeah. This is called first harmonics, second harmonics, third harmonics, but they have a name which is not given to you. It's like the first frequency is called fundamental frequency, second frequency is called, if they are not given the name, it's okay, but there are names for these frequencies which is not mentioned here actually. It's okay, no problem. Just remember first harmonics, second harmonics, third harmonics. Two
Okay.
two fixed and
Yes.
clear to you.
Yeah.
All right. Now let's go to the next boundary condition. See, I'm dealing with only strings, okay? Not with organ pipe yet.
Okay.
I'm dealing with only strings. In next
Yeah.
case, one free end and one fixed end. One free, other is fixed. So you look here. When you have, this is a fixed end, okay? And this is free. Free means it can go up, down. And because
Yeah.
of up and down, you have a wave that can form.
Yeah.
Isn't it? You see here, you can go up and down. Because this part is free, you have this kind of pattern forming, which is the second one.
Yeah.
Even first pattern can form. Okay.
Yeah.
And length of the string is L. Now in this case, for the first harmonics, length is lambda by 4. So frequency is V by 4L. In this case, length is 3 lambda by 4. You have 3/4 of the wave, right? And
Yeah.
frequency is 3C by 4L. Now the change, now you see here, F3, F5. There is some difference here. Okay.
Yeah.
Length is Phi lambda by 4 and the frequency is FC lambda by 2. So these are the first three harmonics of a string with one fixed end and one free end.
Okay.
And I think it has a names. What are those names? Have they given that names here? Okay. Yeah, there's a small difference. The first one is called first harmonic. The second called third harmonic. The
Yeah.
third, fifth harmonics. That's the name that you have to remember for this particular case.
Okay.
But for both the ends fixed, it's first, second, third normally.
Yeah.
The difference. I want you to understand this difference. For both the ends fixed, first harmonic, second harmonic, third harmonic. These are the, okay.
Yeah.
But for one fixed end, it is first harmonic, third harmonic, fifth harmonic.
Okay.
It's only odd, not even. Okay.
Yeah.
Now, I want you to give me something.
Okay.
That thing is, can you give me a general relationship for this? For n is equal to 1 and n is equal to 2.
The wavelength, like they add a half to the wavelength each time.
So what is the general relationship? So let me say, give me a relationship between n is equal to n and
Yeah.
other two things. How it's going to be?
Uh,
I think it's not given in your textbook, but it was given in the previous textbook, like previous syllabus textbook. Oh, it's here.
Okay.
It's here. It's here. It's here. Now it is there down, but I want you to find out.
Okay.
What will it be?
I'm actually not sure.
Okay, let me make it simple for you. First one I'll show you. Second one you tell me. General is L is equal to n lambda by 2,
Yeah.
and Fn is equal to nc lambda and nc by 2 lambda.
Okay.
Okay, and Fn, that means frequency of the nth harmonic is n times the frequency of the first harmonic.
Yeah.
Does these does the first three harmonics obey these rules? Tell me.
Yes.
So n is equal to 1, first harmonic, L is lambda by 2, F is equal to C by 2L, F1 is equal to F1.
Yeah.
For n is equal to 2, it is lambda, Fn is equal to C by L, and
Mm-hmm.
harmonics is 2F1. 2 times. Is it 2
Yeah.
times F1, right? It's 2 times F1 only. Isn't it?
Yeah.
Alright. Now, I want you to do the same thing for the next part. 1 and free. You have the equations written with you, right?
Yeah, I wrote these three equations down.
So then tell me what is the general equation. This is the general equation. This is a general equation for string, both and fixed. Give me
Okay.
three things, same three things for one free end and one fixed.
Yeah.
Workout.
Hmm. Would it be n pi over 4 for the length
And pi
and n pi by 4 and
and lambda.
n nc by 4l for the frequency of the first?
So you're saying n lambda by 4.
Yeah.
Then the last one, Fn, that one,
Fn would be n times nc divided by 4l.
divided by 4L. This one, Fn.
Yeah.
Okay, let us look into the equation.